Hello, this is the second part of sixth lecture of linear algebra, and in this part we return to our topic of diagonalization. But now we consider diagonalization of symmetric matrices and of very special kind, which are called orthogonal diagonalization. Let me state the main result of this part of this lecture, and this is, in my opinion, the main result of this lecture. Okay, we stated first in the language of linear operators. We fix a linear operator from Rn to Rn. And let me remind you that T is said to be diagonalizable if its matrix is diagonal with respect to some basis of Rn. Okay, and now we give a very important definition, very important not only for this course, but for many other courses in mathematics and also for many applications. We say that the linear operator is orthogonally diagonalizable if its matrix is diagonal with respect to some orthonormal basis of Rn. Okay, this is the main result of this lecture. The following two seemingly different conditions are equivalent. The operator T is orthogonally diagonalizable, and the standard matrix of this operator is symmetric. So basically, this result is about symmetric matrices, as you will see a little bit later. Yeah, and we will prove this result using matrices, but it's possible to prove using linear operators. Again, these two different languages are equivalent, but I decide we're going to prove the theorem using language of matrices. Okay, so in order to do this, let me translate the above definition into the language of matrices. If we have a square n times n matrix, we say that matrix is orthogonally diagonalizable. Basically, if it's diagonalizable with additional condition, namely, if there exists n times n orthogonal matrix P, such that P inverse times A times P is a diagonal matrix. If we remove this word orthogonal, then this is going to be a definition of diagonalizable matrices. This is more restrictive condition. This is a stronger restriction on the matrix A. And it will be clear why, because in a second, but first, let me state that the following conditions is equivalent. So this follows from diagonalization criterion. The matrix is orthogonally diagonalizable. One can find orthonormal basis consisting of eigenvectors of matrix M, and matrix M has n orthonormal eigenvectors. Okay, this condition, the equivalence of the three conditions, follows from diagonalization criterion we discussed last week. So, for example, if you remove here orthonormal and in this condition 3, and if you replace it by linear independent, you just get diagonalization condition. But being orthonormal is stronger than being linear independent. N vectors linearly independent if they are orthonormal, but not other way around. Yeah. So again, this proposition immediately follows from the criterion we proved earlier. So we're going to use it. So in order basically to prove the main theorem of this lecture. Okay, so another link we need between matrices and linear operators with regard to this topic, that operator T is orthogonally diagonalizable if and only if its standard matrix is orthogonally diagonalizable. Yeah, this again follows from the diagonalization criterion for matrices and for linear operators we discussed last week. So using this bridge between linear operators and matrices, in order to prove our main theorem of this lecture, it's basically we can prove it either for the standard matrices of linear operators, or we can prove it for linear operators. Yeah. Okay. So translating our criterion on the previous slide into the language of linear operators, we get the following two conditions. The operator T is orthogonally diagonalizable if and only if there exists an orthonormal basis consisting of eigenvectors of T. And if and only if there exist n orthonormal eigenvectors of T. Okay, in some sense, this proposition is easier to deduce from the definition of diagonalization of linear operator T than to then translate from the matrix language. Indeed, so for example, if linear operator orthogonally diagonalizable, it means the matrix of this operator with respect to some orthonormal basis is diagonal. But this means, almost by definition of a matrix of a operator T with respect to some basis, it means that this basis consists of eigenvectors. And since it's orthonormal, it means you have n orthonormal eigenvectors of T. So this more or less almost immediately follows from the definition of orthogonalization, orthogonal diagonalization of the linear operator T. Okay. So, as I already mentioned several times, and I also gave few examples earlier, that many results about linear operators or matrices are easier to prove in the language of linear operators. But psychologically, some proofs may look simpler if we use language of matrices. And this is because of this, I decided to continue using only language of matrices. Maybe this is not a very wise decision, but it's very transparent. It's very transparent. And I think it's less abstract than the language of linear operators. But of course, the proofs are essentially the same because this is basically just two different languages. Okay, first let me consider some example. Or some example of orthogonally diagonalizable matrix. We fix symmetric matrix like this, 5, 5, minus 1, minus 1, and we want to orthogonally diagonalize it. How to do this? Again, we're going to prove some proposition, some theorem later. Let's just see how to basically orthogonally diagonalize in explicit examples. In order to orthogonally diagonalize this matrix, first, you need basically to follow the same steps as usual diagonalization. First step, find a characteristic polynomial. You compute characteristic polynomial. In this case, it's not very complicated. You can factor it immediately in like this. So you deduce that eigenvalues are 4 and 6. And then you find eigenvectors, which correspond to eigenvalues 4 and 6 respectively. So this is absolutely the same strategy, the same algorithm as we did for diagonalization. So if you were asked to diagonalize this matrix, the only thing you have to do, you have to take these two eigenvectors, form a matrix out of them, say matrix M, and then you can deduce that M inverse times A times M is diagonal matrix with entries 4, 6. Yeah. But now we want to orthogonally diagonalize matrix A. So this matrix M, which I just mentioned, has to be orthogonal matrix. In order to do this, we have to find orthonormal matrix with orthonormal columns. So it means if these two vectors were orthonormal, I can just repeat the same step and I get orthogonal diagonalization. But of course, they're not orthonormal. Why? Because the length of this vectors is root 2, length of this vectors is root 2. Why did I choose these vectors? Because why I choose these eigenvectors with eigenvalues 6 and 4? Because they look simple. They look simple, but they're not orthonormal. Yeah. However, you may notice, and this is not a coincidence, this is a part of a theorem, that these vectors are actually orthogonal to each other. So if you have two orthogonal vectors and you need two orthonormal vectors, this is very easy to do. Yeah, you just need to scale them a little bit. I could scale them from the beginning because there are no specific choice for eigenvector for given eigenvalue. If I take in any of these eigenvectors and I scale it by non-zero scalar, then I get also eigenvectors with the same eigenvalues. Just pick these two vectors because they're simple. Okay, but they're not orthonormal. But we can scale them. How to scale them? You have to divide them by the length. Okay, and you divide them by the length. You get this vector √2 over 2, √2 over 2 instead of this, and you get this vector instead of this. Yeah, these are also eigenvectors with eigenvalues 4 and 6 respectively. But now the matrix for the diagonalization is orthonormal, yeah, because its columns are orthonormal. And you can check that P inverse A times P is 4006. Actually, this is very easy to check. Why? Because inverse of P in this case, it's easy to find. So for example, if I form a matrix out of these two vectors, then in order to find the inverse of this matrix, I have to do something. I have to use a formula, or anyway, I have to find the inverse. To find the inverse of this matrix, it's very easy. You just need to transpose it. Yeah, so you just transpose it, put it here, take A times P, and you check this is diagonal matrix with a diagonal entries 4 and 6. Okay, now let's go to the proof of main result. Let me restate it accurately in the language of matrices and proof. Okay, so the first part of the proof, and this is given by this lemma. Every orthogonally diagonalizable matrix must be symmetric. Okay, how to prove it? Okay, basically by definition, you take a square, n times n matrix A, you assume it's orthogonally diagonalizable. What does it mean? It means that there exists orthogonal matrix P such that P inverse times A times P is diagonal matrix D. But keep in mind, the diagonal matrix, by basically definition, is symmetric. So here we have symmetric matrix, yeah, and we want to prove that A is symmetric. But let's rewrite this. We can rewrite this equality in this way, yeah. We just multiply by P inverse on the left and by P on the left by P inverse on the right. And you get A is P times D times inverse of P. But inverse of P is transpose of P because P is orthogonal. So you get this. Okay, so A looks like P times D times transpose of P. So we want to prove that A is symmetric. To do this, you just need to take its transpose and check that it is equal to A. Okay, this is done in this line. You take A transpose, and this is transpose of this guy. But then again, transpose of a product of matrices is a product of the transposes taken in the opposite order. So transpose of this is just product of transposes of these three matrices. But D is symmetric, so transpose of D is D. D is diagonal matrix. And transpose of P, yeah, transpose of P is just P. So here we get P, and here we get transpose of P. But this is exactly matrix A. Yeah. So we proved. Okay, so every orthogonal diagonalizable matrix is symmetric. Okay. Now we want to prove the opposite assertion, which is basically translation of the our main theorem into the language of matrices. The matrix is orthogonally diagonalizable if and only if it's symmetric. We already proved one direction, so of the theorem, if matrix A is orthogonally diagonalizable, it implies it's symmetric. This was easy direction. Now we're going to prove the difficult direction, that if A is symmetric, then it's orthogonally diagonalizable. Again, the theorem is just the translation of our main theorem about orthogonally diagonalizable linear operators into the language of matrices. Okay, good. So the theorem has a very simple corollary that if at some point you see diagonal matrix, not diagonal, if you see symmetric matrix, you don't need to check that it's diagonalizable. It is diagonalizable. Even more than this, it's orthogonally diagonalizable, but in particular, it's diagonalizable. This is very handy. Okay, so as I already said, we proved one direction of the theorem. Let's prove another direction. And the key step in the proof of other direction of this theorem is the result which we proved last week during the last lecture, the result about basically Hermitian complex matrices. And as a corollary of this result, we get that every real symmetric matrix has at least one real eigenvalue. Let me remind you that this purely real theorem have been proved using complex matrices. It's actually not easy to prove this theorem using just real matrices. To be precise, we proved that every real symmetric matrix, if you take its characteristic polynomial, all its roots are real. So in particular, it has at least one real root. This is a very special corollary of our result. Yeah. Okay, we proved this last week, so now we can use it. Why we can use it? Because we want to prove this direction of this theorem by induction. Okay, it's going to take few slides. Its proof is actually not so difficult on the level of ideas, but maybe it's a little bit difficult in the way it is presented. So I strongly suggest to read the proof in the lecture notes, where it's given with more details, or try to prove it by yourself, because when you first try to prove some result by yourself, and at some point maybe you get stuck, it's easier later to read the proof. When you read the proof from the very beginning, sometimes actually it may look too abstract or too dry, but when you already try to prove something by yourself, it's much easier to read the other proof given by some other person. Yeah. Okay, so let's prove. So we fix n times n symmetric matrix. We want to show that it's orthogonally diagonalizable. We want to do this by induction on n. The base of induction is 1 times 1 matrices. 1 times 1 matrices are symmetric by definition. So, and they are diagonal by definition. So because of that, there is nothing to prove. Okay, but anyway, the assertion of our theorem definitely true in this case. Yeah, so this is base of induction. From now on, we assume that n bigger or equal than 2, and we assume that the result, our theorem, holds for all n minus 1 times n minus 1 square symmetric matrices. We assume that all symmetric matrices of size n minus 1 times n minus 1 are orthogonally diagonalizable. This is our induction assumption. Okay. So, in order to use this induction assumption, we have to use the theorem on the previous slides. We know that this matrix, our symmetric matrix A, has at least one real eigenvalue. And since it has one real eigenvalue, it by definition means that there exists eigenvector with this eigenvalue. So there exists vector, non-zero vector v1, such that a v1 equals to lambda 1 v1, where lambda 1 is eigenvalue. Okay, v1 is a vector. But then, as I said, there is no unique choice of an eigenvector. Once you fix the eigenvalue, you can scale it. So now we scale it in such a way that its length is 1. So basically, you just take any eigenvalue and you divide it by its length. Yeah. Okay, so we got one vector v1 which is orthonormal, just one vector. Yeah, but now we use the results from orthogonality properties of vector spaces, which we proved a long time ago already. So if you have several orthonormal vectors in n-dimensional space, you can extend this collection of vectors to the orthonormal basis of this n-dimensional space. So we just we can find n minus 1 vectors, v1, vn, such that our n vectors from v1 to vn are orthonormal, and since there are n of them, they form an orthonormal basis of our vector space. Okay, the first vector v1 is an eigenvector of A with eigenvalue lambda 1, but all the remaining vectors in this collection are more or less some vectors. They are not eigenvectors of matrix A. We just more or less almost randomly choose them. Again, this extension step is absolutely not canonical, absolutely almost random, almost error. It's not, of course, completely random because we want this vectors to form an orthonormal basis, but there's a lot of choice in the vectors v2, v3 up to vn. Okay, good. So now we want to take a look how our matrix A, how the linear operator which correspond to the matrix A, this, if you remember this Gothic T A we use, how this linear operator looks like in this basis. But in the language of matrices, basically, we just want to form a matrix out of these vectors, and we want to replace A by this M inverse AM, where M is a matrix with columns consisting of these vectors. Yeah, and if we just get lucky, if all of this v2, v3 up to vn are eigenvectors of matrix A, then we should get diagonal matrix. But in general, we would not get it, but we get something close to it. Yeah. So we take this matrix. I said M, now it's actually by Q. Yeah. And because it's a temporary matrix, this is not the matrix we're looking for. It's just intermediate step. So by definition, Q has orthonormal columns. So by the criterion proved in the previous part of this lecture, the matrix Q is orthonormal. Okay, orthogonal. Now we basically try to follow this diagonalization step. We try to replace matrix A by this matrix, Q inverse AQ. Again, if we just lucky and v2, v3 up to vn eigenvalues, then this matrix must be diagonal, and we are done. But probably they are not. So we get some matrix, but it's a little bit simpler than matrix A. Why? Observe, by the construction, if you multiply this matrix by vector E1, you get lambda 1 times E1. Indeed, look what happened when you multiply Q by E1. You get vector V1. Yeah, if you multiply Q by E1, it's exactly the first column of the matrix Q. So you get V1. So Q times E1 is V1. But AV1, by our assumption, is lambda 1 times V1, because V1 was an eigenvector with eigenvalue lambda 1. So we get this product AQ E1. This is lambda 1 V1. But on the other hand, if you multiply everything by vector Q, you get lambda 1 Q E1, which is, as I already said, is just V1. So we get exactly what we're supposed to get. We get lambda 1 V1 equals to lambda 1 V1. Yeah, okay. Or you can say, if you multiply inverse of Q, if you multiply by V1, then you get a vector E1. Why? Because Q E1 is V1, so inverse of Q times V1 is E1. Yeah, you just multiply. Okay, so we have this. But this basically means that E1 is an eigenvector with eigenvalue lambda 1 of this matrix. And by basic properties, so when you multiply E1 matrix by E1, you get its column, first column. So what we just proved, that the first column of this matrix is just lambda 1 E1. So it's this matrix has all entries in the first column except the first entry are 0. Okay, yeah, good. On the other hand, this matrix is symmetric. Why? By definition, we have to check. You take this matrix, you take its transpose, you want to prove that it's the same matrix. You take a transpose, transpose of product of transposes taken in the opposite way, you get this product, but then transpose of transpose is just get a matrix Q, yeah, and you get this matrix, but this is exactly the matrix we have, yeah. So this is symmetric matrix. We proved that this is symmetric matrix whose first column is lambda 1 0 0 0, but it means that its row is the same, lambda 1 0 0 0 0. Okay, so it means that our matrix looks like this, yeah. So we did some minor transformation to the matrix A. We replace it by this matrix, which is also symmetric, but it looks simpler. Yeah, it looks very simple. I mean, it's not very simple, but it's definitely simpler than before. Look, if we are in 2 by 2 case, we are done. Yeah. If we're in 2 by 2 case, we actually done. Why? Because we get diagonal matrix. This is exactly what we're looking for. Q is orthogonal matrix, and this is diagonal. Yeah, but we're not necessarily in 2 by 2 case. We may be in 3 by 3 or 4 by 4 case. So we have to proceed. But this is basically inductive step. This is inductive step. We already know that this n-1 times n-1 matrix is symmetric, so it's orthogonally diagonalizable. And now we just basically need to cook up n times n matrix of orthogonal diagonalization for this matrix using our inductive assumption. So this is done in the next part of this slide. Yeah. So we denote this n-1 times n-1 matrix by A tilde. It's symmetric, yeah, because the big matrix is symmetric. So it is orthogonally diagonalizable. So we can find some matrix Q tilde, orthogonal matrix Q tilde, such that Q tilde transpose times A tilde times Q tilde is a diagonal n-1 by n-1 matrix. Here we use our induction assumption. Okay, and now we just need to convert this n-1 times n-1 orthogonal matrix Q into the n times n orthogonal matrix. But we can just basically put 1 in the left top corner and then put 0 everywhere. Yeah. Instead of matrix Q tilde, we form this matrix here. Since Q tilde is orthogonal, then of course this guy is orthogonal. Yeah. And we observe that what happens if you multiply our matrix Q transpose AQ times by R on the left and by R transpose on the right, because first row looks like this, 1 0 0, and the first column looks like this, 1 0 0 0. Nothing happened with the first row and the second row of this matrix. It's going to be the same. But this n-1 times n-1 part, it's basically going to be just our matrix A tilde multiplied by Q tilde on the right and Q tilde transpose on the left. And we already know that this part is diagonal. Okay, so we get diagonal matrix. So the only thing now we need to check, first of all, that R is orthogonal, which is actually more or less by definition, almost by definition, and by the fact that Q tilde is orthogonal by assumption. And then we have to use the fact that product of orthogonal matrices is orthogonal. So for our matrix M that we were looking for orthogonal diagonalization, we can choose Q times R. Okay, good. So we called it P because usually called M matrix for diagonalization. For orthogonal diagonalization, traditionally we reserve. It's quite often people use letter P. Yeah. Okay. So we put P to be Q times R, and then this is diagonal. We proved. We only have to check that Q times R is orthogonal, and then we're done. Okay, I put it here. This is the final easy part of the proof. So we already know that Q is orthogonal, R is orthogonal. We need just to check that R transpose times R is identity, but this is R transpose, this is R. When you multiply matrices like this, formed by these blocks, basically you multiply the blocks. You're gonna have 1, because it just comes from 1 multiplying this row by this column. So you get this. And then in this block, you're going to have just a product of these two n minus 1 times n minus 1 matrices, which you already know is identity because matrix Q tilde were chosen to be orthogonal by assumption, inductive assumption. So we get identity. Okay, good. So our matrix P is orthogonal because R is orthogonal, Q is orthogonal, and we proved in the previous part of this lecture that the product of orthogonal matrices is an orthogonal matrix. Okay, this completes the induction, and this completes the proof of the theorem. Okay, so basically this is main part of this lecture, in my opinion. This is very important result. So now let's just see how we can do orthogonal diagonalization in examples. We already did one 2x2 example, which is nice, but let me just repeat it because we did this example before the proof. Now let me consider another example after the proof, which illustrate the proof. So let us take this 2x2 symmetric matrix, and we want to orthogonally diagonalize it. How to do this? Again, we just follow the same steps as for usual diagonalization, but we have to be sure that the matrix we're going to find for diagonalization must be orthogonal at the end. Okay, so first, the same step, you must find a characteristic polynomial. You find characteristic polynomial. This is determinant of the matrix A minus lambda I. And then you have to factorize it like this. Basically, you have to find its roots. Yeah, and its roots all real by the theorem I mentioned today, which we proved last week. And it's, of course, we know this theorem here because we found all these roots. These roots are 2 and 8. They are eigenvalues of A. Okay, and then we find the eigenvectors that correspond to these eigenvalues. And we already know that they're going to be linearly independent. We know this from the previous week because they correspond to different eigenvalues. But we also know from the basically proof of our theorem, which we just gave, that this vector is going to be orthogonal. So you can take any eigenvalue with eigenvalue. You can take any eigenvector with eigenvalue 2. You can take any eigenvector with eigenvalue 8, and these two vectors are going to be orthogonal. Yeah, because these two eigenvalues are different. This follows from the proof of our theorem. Okay, now we only need to scale them to get orthonormal basis. So we scale them like this. We found these two representative. Okay, and you see they are orthogonal and they have length 1, so they are orthonormal. Yeah. So we form the matrix P out of them. We put this vector as the first vector of our matrix, first column, and this vector second column. And because these columns are orthonormal, the matrix is orthogonal. Yeah. And if you wish, you can check that this product P transpose AP, which is the same as P inverse of P times A times P, that it's diagonal with diagonal entries to 8. But this follows from the proof of our theorem, yeah, and from the diagonalization process. Okay, this is it. Let's consider 3x3 examples. Let me just consider 3x3 examples so I show you one small shortcut, which may save you a few minutes when you consider similar problem by yourself. Okay, consider 3x3 examples. Example, I take this matrix, it's symmetric. Again, if a matrix is not symmetric, it's not orthogonally diagonalizable. You should not even think about this. It may be diagonalizable, but definitely not orthogonal if it's not symmetric. But this one is symmetric, so it's definitely orthogonally diagonalizable by our main theorem of this lecture. So we just need to find such matrix P such that P transpose AP is diagonal and P is orthogonal. Okay, we already know that this lambda 1, lambda 2, lambda 3 are eigenvalues of my matrix A. Okay, so to find this matrix P, I have to find, first of all, these numbers. These numbers are the roots of characteristic polynomial. Then for each of these numbers, I have to find corresponding eigenvector. And then I take these eigenvectors and try to cook out of them orthonormal vectors with in the same eigenspaces. And then I put this resultant orthonormal vectors as a columns of P. And I'm done. So let's just do this. It's very similar to the previous example, but still let me do this. I compute a characteristic polynomial as determinant of this matrix. And then, okay, this is a little bit different step. I mean, it's the same step, but it's maybe a little bit more difficult than 2 by 2 case, because if you have 2 by 2 case, your characteristic polynomial is quadratic, and you have a formula for the roots of quadratic equation. But in this case, polynomial going to be cubic. And the formulas for the roots of cubic polynomial are extremely complicated. So if you encounter a problem like this, it's in this course, it's very likely that the roots are nice. Nice means integers. So, for example, if you know that the roots are integers and all coefficients of your matrix are integers, then keep in mind that the product of roots are basically a determinant of the matrix A, and this is a constant term of your characteristic polynomial. So your integer root, if it exists, must divide the constant term, and of course, if all coefficients are integers. Yeah, and this helps you to find a root. Yeah, of course, if you have access to any computer software, you can just take this polynomial and write factor. And if your polynomial has a nice root, like integer or rational, any computer algebra software going to be able to find it. This is easy. Okay, so in this case, roots are relatively simple, like this. They are your real eigenvalues of your matrix A. All of them are real. We know that by the theorem proved last week that all roots of characteristic polynomial of symmetric matrices must be real. Yeah, and good thing that they are different. And we already know that the corresponding eigenspace is going to be one-dimensional. Yeah, and we know this from the results of the previous lecture. And we know that the corresponding eigenvectors, which correspond to this eigenvalue, is going to be linear independent. So basically, I just need to find one eigenvector for each of this lambda. And by the theorem on the previous slide, the theorem we proved earlier in this part of this lecture, these eigenvectors going to be orthogonal to each other. So the only thing I have to do is just to scale them to make them to be of length 1, and then I get my orthonormal basis consisting of eigenvectors of matrix A. That's it. Okay, let's do it for lambda 1 equal minus 9. Let's just, okay. We choose the first eigenvalue, and to find a non-zero eigenvector, all eigenvectors are non-zero. Basically, to find the eigenvector, we need to find non-zero vector in R3, which satisfies this equation. This is more or less equivalent to the definition of eigenvector with eigenvalue lambda 1. Okay, we substitute here lambda 1 to be minus 9. We solve system of 2 equations, 3 unknowns, and we find one eigenvector, yeah, with eigenvalue minus 9 and 1. Okay, with minus eigenvalue minus 9. Okay, for example, if I were doing diagonalization process, not just orthogonal diagonalization, I would probably, instead of this vector, I would probably choose 2, 1, 2, because it just looks simpler. But 2, 1, 2 is not going to have length 1. Its length is going to be 3. So now I choose a vector. I just scale the vector 2, 1, 2 by 1 over 3, and then I get vector with length 1. Okay. Then I can do the same for lambda 2. I get another vector, and I could do the same for lambda 3 to find the third vector. But here is a short cut, small shortcut. So once I found V1 and V2, I know that V1 and V2 must be orthogonal by the proof of the theorem which I gave earlier today. But I also know that the third eigenvector with eigenvalue lambda 3 must be orthogonal to both of them. And now I can use a shortcut. I can just take the cross product of V1, V2, and I must get vector, which is eigenvector of my matrix A, and orthogonal to the previous two. So it must be eigenvector with eigenvalue lambda 3. Yeah. And if this two, since this vectors V1 and V2 has length 1, this cross product automatically has length 1. Okay, I just take a cross product. Again, this is just a shortcut, which saves you maybe a few minutes of computations. Yeah. You can of course proceed as for the when we found vector V1 and V2. Okay, good. So we take three vectors, V1, V2, V3. You form a matrix P out of them. You just put them as columns of this matrix P. And this is a matrix you can use for your diagonalization. Yeah, you can just check that P transpose times A times P is a diagonal matrix with entries -9, 36, and 18, respectively. Okay, this is basically all about orthogonal diagonalization. Let me stop this recording, and let me just mention that this is the last topic that's going to be examinable. The third part of this lecture is about conic sections, which is basically application of orthogonal diagonalization. We're going to classify conics in the plane, conic curves in the plane. But this topic is conics not going to be examinable. This is just illustration of the methods we use. But this topic, orthogonal diagonalization, is examinable. Yeah, okay, good. Let me stop the recording.